Thank you for being interested in this video. My name is Rafael, and the topic of this presentation, convolutional neural networks, or CNNs, and transfer learning is something that was not very common in our field, geoscience and geophysics, a few years ago, but is actually very popular right now. So it's likely that you're at least familiar with it. But anyways, I hope there's something interesting for you here, something different. And I have this slide here to remind ourselves that CNNs, convolution, are an operation that can be taken in different dimensions, right? So I have one example here showing a case in which we use 1D CNN to forecast the increase of high energy electrons in Earth's outer radiation belt. So this is a 1D CNN. A lot of CNNs are used to process 2D data images. So maybe that's the most common one. And now a lot of 3D CNNs are used as well for seismic data. So there are several examples using 3D CNNs for fault segmentation or salt segmentation. I also have this slide here to remind us that convolution are actually an operation that's been around for a while. And it's very popular in image processing. And I want to show what happens here when we have an input. So this is the size of the input, 299 by 299 pixels. This is an RGB image, a remote sensing image of an oil well. And we can see the shadow here of the pump jack. So what happens when we get this data here, this image, and we convolve it with these different filters here. So these are the values of the filter. And this is the output we get when we do this convolution, right? So some of them you're going to see are going to highlight vertical edges. Some are going to highlight horizontal edges. This one, in this case, is going to highlight all the edges. Some of them are actually quite subtle, the changes they do in the input. So in this case here, just if we do a blur in the red channel, the output is very similar to the input. Just the colors are a little shifted, somewhat changed. One of the main aspects here, the main difference between traditional convolution used in image processing and CNNs is that for image processing, someone thought about the values to add to these filters and how to set up these filters based on the results they wanted to get. In CNNs, the values of these filters are usually started with random numbers. So this is one example. What happens when we get this input, we convolve it with a random kernel, a kernel with random weights. We get this output, and again we can see the output is actually quite similar to the input. And through a process called training, the values here, they changed based on the objective we set to that model, right? And I'm going to try to illustrate that with this very simple task here. So I set up a very simple data set with a handful of examples of 3 different classes that are actually very different from each other. So I have a class here that I'm calling fossil. And these are images, RGB images, pictures of pink sections of user units. Then I have oil well images here. So these are remote sensing images for oil wells. So these two are naturally 3 channels RGB images. And I also created a pseudo RGB class based on seismic data. So these are images from the Cora volcano. These are time slices from the Cora volcano. And you can see somewhat rainbow colors here. And the way that I set up that was to simply select 3 consecutive time slices from the volcano, right? So you can see the circular shape of the volcano here, maybe some faults here. And that's how I set up a pseudo RGB. So what I want to do now is to set up a model that is able to look at each one of these images and tell me what is the class that image belongs to. And looking at that, we can see it's very easy because they're very different from each other. So we can actually use a simple model to perform that classification. So this is one way to represent CNNs. There are different ways to represent them. And I'm going to walk you through this representation. So in this CNN, we're going to have mostly convolution operations, and the size of the filters for this convolution are 3 by 3. and they are followed by a non-linear activation function. In this case, is the rectified linear unit. And I'm also using max pooling operation. In this case, the window is 2 by 2 and the stride is 2. So what happens when we do that is that we reduce the dimension, the spatial dimensions by half. So we're going to have an input here. It's 100 by 100 RGB image. So 100 by 100 pixels, 3 channels. And we're going to have one output here that is one of each one of those classes that I just mentioned in the slide before. So for the first layer, I'm going to get these 3 channels here. I'm going to apply a set of convolutions, and I'm going to generate 8 feature maps. So the output of the convolutions are called feature maps. So when we're doing the convolution here, the size, the spatial dimensions, they stay the same. But then we apply the max pooling operation, and we're going to reduce the spatial dimensions in half. The number of channels here stays the same. Then we apply convolution again, and we increase the number of channels, the number of feature maps from 8 to 16 here. And we continue doing this process for convolution and max pooling all the way to this point here, in which we have feature maps that are 25 by 25 pixels, and we have 32 of such feature maps. Then we perform an average pooling operation that's going to collapse this information here, the 25 by 25 pixels, into a single pixels. And we remain with 32 channels. And this is going to be input to a final layer that's going to perform the classification. So this is just reshaping what I just showed you. And what we're going to see here is that, again, the input has 3 channels. Then we're going to perform a convolution, and we're going to get 8 feature maps from the first layer. So just to be clear here, these are the feature maps that I'm going to show. I'm not showing the weights of the convolutions. Then we have a max pooling operation here and another set of convolutions. So we're going to get to this point with 16 feature maps, and the size here is half. The size here is half of what was before. And we do the same convolution and max pooling. So we get now with 32 feature maps. The size is half of what was before. Then we're going to perform the average pooling here, and we're going to collapse all the information from this 25 by 25 pixels into a single pixel. I'm using the same size here, but just to remember, this has a spatial information, this one doesn't have it anymore. And that's going to be the output for the final read. So just to reshape again, this is what we're going to see. So if we have an untrained model, this is what happens when we add one input to that untrained model. So I set up the model that I just showed you. The model has random weights. I get this image and I fed it to the model. So this is a forward pass. And these are the feature maps, the output of the different layers that I just showed you. So before training, we have epoch 0. So one epoch is one pass through all of the training data, right? At the bottom here, I'm marking what is the probability of the classes that I want to achieve. So when we start training, before training, we're going to have values here that are somewhat similar to each other. What we want actually is this number to be large and this number to be small, right? So I want this number to be close to 1 and this to be close to 0. They're not. So I compute the loss here across all the samples, and I have this value. And using that loss, I can also use the backpropagation algorithm and compute the gradients of the weights. I'm not showing the weights here, just the feature maps. I can compute the gradients of the weights. And using some sort of optimization technique, very often, most of the time, some sort of gradient descent, we can update such weights, and we can update the weights in such a way that in the next pass, we're going to try to be closer to 1 here and closer to 0 for this values here. So we're going to see how that happens now during training, right? So this is one example of the fossil. And I start training here. So we're going to see the loss is going to reduce. The accuracy is going to increase. I forgot to tell you about the accuracy, but it's simply the ratio between the total number of, is the ratio between the correctly classified samples over the total number of samples we have. So the training is complete, and we see now by the end of training, we actually get a number here. We get what we wanted to get, right? So this number is closer to 1, and these numbers are closer to 0. And during training, we're going to see all these feature maps changing, right? Um, based on the changes of the weights of the model. So I have another example here for the oil well, and we can see how that changes and how this first layers here, these first feature maps are actually quite similar to the input itself. By the end of training, again, we get what we want to get. And the final example that I have is for the seismic data. And one thing that I want to highlight here is what I told you at the beginning, that when we get to this point here, we still have spatial information, but then we collapse it into a single pixel here using the average P. In the end, we still get a good accuracy, I mean, a high probability for this sample here. And we can see how all the circular shapes are highlighted by the model. So what I showed is actually a very easy image classification task, right? It's very clear that a seismic is not a fusilineate. The colors are very different, all the shapes are very different. In reality, research is conducted for problems that are actually more challenging. So in this case here, I'm showing some examples of the ImageNet large scale visual recognition challenge. And for that task, the objective is not only to tell the difference between a bird and a cat, but to be more specific, right? So, and tell the difference between, for example, a Persian and a Siamese cat. So that's actually more challenging. And to do that, we need to use models that are more complex than the ones that I showed you. So this is one example of a VGG, and the general structure is still pretty similar to the one that I just showed you, right? We have an input on the left, and we use mostly convolution max pooling operations, and we get the output on the right here. But note the difference here. The input has 3 channels, just like as we were using, but then the number of filters, the number of feature maps is much larger than the one that I showed you before. So other CNNs are actually, they use different paths for the information to flow from the input to the output. So this is inception. You can see different paths here and how they're concatenated, always trying to achieve a better model for that data set. This is one example of the residual network. So this is quite popular nowadays. A lot of architectures are actually variation of this strategy to have a path flowing, jumping some connections to help with the gradient vanishing growth. So now that I explained a little bit about training, and I want to talk a little bit, how can we explore all this effort that has been put into developing models that are good to classify the ImageNet, that is a data set with 1 million image, right? 1 million images. So there's this technique called transfer learning, in which we repurpose part of a trained model to perform a new task that depends on your data. And there are several applications that can be done with this technique, right? And these are some examples of applications in which we were successful applying them. So we used CNNs for classification of microfossils and core images and thin sections, and also hand samples. And I'm going to quickly walk you through some of these examples. So one example in which we were successful in applying transfer learning and CNNs is for classifying little fishes in core. So what we did at the time was there are different ways to do that, but what we did at the time was to use standard photographs of core, and we used a running window technique to extract smaller crops of the rock. And the objective of the model was to look at each one of these smaller crops and provide a classification for that crop. What I'm showing here with this green arrow is something that I didn't mention yet regarding the testing data. So what we did here was to make sure that when we selected something to be part of the test set, its neighbors were not part of the training set because trying to avoid label leakage. So the test set is important to try to understand how the model would perform with similar data. It was not used in training. So, and all the results that I'm going to show from now on are actually based on the test set of the experiments we used. And we can see here for different classes, and I apologize, I have the numbers here, but the name of each one of these classes is quite large. You can see the examples here. So different classes, the probability that the model assigned for that crop. And we can see sometimes the model is highly confident in the same class as the geologist assigned. Sometimes the model is less confident, but inevitably the model is going to make mistakes. And at that time, a point that we raised was this one, that using this image as input to the model is quite confident that almost 70% probability assigned for skeletal grainstone class, but this is actually a picture of the carpet in Sarkis and 8th floor. However, when we look at the training data for the skeletal grainstone, we can understand why the model made that mistake, right? We can see the colors are similar. Some of the images, they have this horizontal structure. So that's understandable. Anyways, that's just a reminder that we always have to check and make sure if what the model is outputting makes sense. The other example that I have is actually how I started into this, was to use CNN for fossil classification. And in this case here, I want to remind a little bit of transfer learning. So a few slides ago, I said that transfer learning is a technique in which we repurpose part of a trained model to perform a new task that depends on new data. There are different ways of doing that. One way I'm calling here feature extraction. So we're not going to update part of the model, and we only train the new part of the model. And the most used one actually is sometimes called fine tuning. And to do that, most of the times we start updating the new part of the model, and eventually all the model is free to learn, and we train the entire model. And using a fine-tune technique, we actually got good results for the fusion init. So these are fusion inits. The way that this image is set up is that the title of the image here is the genus that was provided by the original publication. And the box below here is the class that was assigned by the model. So the class is actually the genus here. And I'm saying class in the machine learning meaning and not in the biological meaning. So the box is green when they are the same. And we can see a lot of examples in which the model assigned a very high probability to this correct class. And the box is red when we have a wrong genus assigned by the model for that image. And this is a summary of the experiments we did with that data set. And I'm going to walk you through it again. So feature extraction and fine tune are these two different ways of transfer learning that I just mentioned. Randomly initialized weights is the traditional training when we have a model that was set up with random weights, right? So I'm going to ignore VGG a little bit, and I'm going to highlight here that fine tune was always much better than all the other approaches for the classification of the fusion init data. So this is the accuracy of the test set. This is the 80% mark here. When we look at the VGG, we can see right away that there was something weird that happened when we shifted from the feature extraction to the fine-tune part. So when we released the model to learn, it actually collapsed, and we didn't recover after that. So there are ways to fix this, but because in that case we use the standardized hyperparameters for all of the experiments, we didn't investigate that further. But anyways, we can see that fine-tune is always helpful, especially when we compare it with randomly initialized weights. So one thing that comes to mind here in all these examples that I showed is that the CNN models were primarily trained on the ImageNet dataset. And I have some examples here of that dataset, right? So the intra-class variability is actually very large. So this is one of the class of the ImageNet, Stewart Bridge. And you can see the images are very different. They have different resolution. The object to be classified has different colors, and there's occlusion. For example, in this case here, the background is different. The colors of the object themselves are different. So this is very different. For example, this very large variability, it's not the same that we find, for example, when we're dealing with thin section data. So thin sections, even when we have thin sections that are imaged through different magnification levels, so this one has a higher zoom compared to this one, they are much more behaved when we compare that to ImageNet that has such a large variability. So what David and I did was trying to understand if we could select a model that was more closely visually similar to the secondary data set that we're interested in classifying, if we could achieve better results by training a CNN model in that data set first. And that was actually Dr. Marford's idea and suggestion. So we selected 3 different data sets here with varying sizes. So we have the first one here, MSS versus MSI versus MSS. These are actually thin sections as well, but these are histopathological images. So I don't know very much about cells, but these are cell nuclei. Then we have the raw foot, so raw foot texture data set with 25,000 samples. And these are simply images of raw food taken under different lighting conditions. So this is the chickpea, this is also chickpea, but the lighting is different here. And finally, we have the ham 10,000 data sets. And these are images of skin lesions. So this is a dermatoscopic data set. So our idea here was that these data sets, they are much more similar to thin section than the ImageNet that has such a large variability. So our idea was that if we train a model to classify that data set, these data sets, and transfer them to the thin section classification problem, maybe that will be better than getting a model that was pre-trained on ImageNet. However, that was not what we found. So the way that this image is set up here is that we're going to see here the accuracy for the test set, and we have different tests here. The size of the bar here shows the mean average of the accuracy across multiple experiments, varying the hyperparameters for training the model. The bar here shows the minimum value and the maximum value achieved by this variation of hyperparameters. So the baseline is when we have a model that has that is initialized with random weights. And then we have here ImageNet, meaning we got a ResNet 18 model, pre-trained on ImageNet and fine-tuned on the classification of thin section data. So we have ImageNet. This is the one of the most easily accessible datasets, pre-trained models you can download. And then we have the examples that we propose for these experiments. So we pre-trained the model in each one of these 3 different datasets. So what we see right away is that models pre-trained on ImageNet, they achieve a much better performance, and they also seem to be much more stable than the other. So almost all, even varying all the hyperparameters, we still get like very good results for the classification of thin sections. We can also see in this case here that a smaller data set, a smaller model architecture, so ResNet 18 has 18 trainable layers, was better for, in our case, than a larger model. So ResNet 50 has 50 trainable layers. So our understanding is that the model doesn't have enough variability. I'm sorry, the data set doesn't have enough variability, and training a larger model actually is harder in that case. Anyways, still pre-training a model in ImageNet was better than any of the other options. And I hope this presentation was helpful to show that transfer learning is helpful when we're training CNN models for the interpretation of geoscience images. And our interpretation, especially for this last slide that I showed you, that it's better when you have models that are pre-trained on large data sets and they have, and the data sets having high intra-class variability, for example, the ImageNet, are actually very helpful when you're trying to fine-tune models. And as I showed you for the core classification test, the implementation discussed here is always going to assign something. It's always going to assign an output for whatever image you analyze. And in contrast, a geoscientist has a deeper understanding of what's going on and can make more informed decisions. And also remember that CNN can only successfully classify data with similar characteristics as the samples in the training set. And that also reflects what we get with the carpet, right? So whatever you went to the model is going to provide you with an output. And you can only trust the output if it's actually, if the data that you're processing is similar to the one that was trained. And thank you. I hope this was helpful for you.